Okay, again, before I forget, no class on Thursday. Today we're going to go ahead and get into our material known as graphs or graph theory.
All right, let's go.
All right, graph. This is graphs are used everywhere. Yeah.
Where do we? Quick question. Where do we? If we're not turning in like the ethics paper like in class, where do we turn it into?
Just get up wherever. Just put it on there. Just turn in your ethics
Just put
paper.
it somewhere. Yeah.
All right, graphs are used everywhere to represent all sorts of things. Google uses it to do your shortest path when you're trying to go somewhere. But let me give you a quick explanation of what a graph is. So with a binary tree, you usually have a root node, it goes to another node. You might have another node right here, which can go to a node, go to a node, boom. Okay? So, by the way, all trees are graphs. Okay?
All trades.
All trees are
Not
graphs.
all graphs.
But not all graphs are trees. For example, you could have this node go back up here.
What?
Now it's a graph.
Wait.
All right?
Yes.
So beforehand, this was a tree because you had a root node. Okay, you know, trees have roots. But a graph doesn't have a root node per se, or you can just think of every node as the root. And so they're all connected. You might have cycles. You might be able to span everywhere, or you might be, you know, randomly disconnected. Like you could have, we can make this node orphaned.
Oh.
Oh, and then you could go to another node for some reason, which could go over to this guy. That's still a graph. So we're just breaking loose with this diagram and saying, you know, arrows can just go everywhere. To any node, you got it there. Okay?
Nice.
All right. So that's a graph. Okay, cool. You good? I mean, you understand what I'm saying? Oh, yes, that's true. Don't worry. It turns out to not be too bad. Oops, I'm on the wrong slide. All right, blah, blah, blah. Okay, great. Let's go ahead and go. Okay, the book goes through a classic introduction called the, who wants to try and pronounce it?
Königsberg.
That was a good guess. I have no idea how to pronounce that word. Cone. The bridge problem. The river, is that Pringle?
Pringles.
Pringles? Yeah, I know.
Pringles. It's a Pringles chip in the middle.
Wow, we are so internationally intolerant or whatever I'm looking for. All right. Flows through the Isle of, oh my goodness. Whatever. Neat? Yeah, sure.
Neat.
And then divides into two branches. So you got bridge going to from D to A, and then you got other bridges here. Okay? So the question is, can you start at any point and visit every bridge exactly once? I mean, good.
Wait, can you repeat that?
Is it possible to start anywhere? You can choose any point and then go and visit every bridge exactly once. So you could go F to G to D to E, but then you couldn't go anywhere because that would be going over another bridge. Going over a bridge twice. Yeah, maybe you could.
Yeah, you could go A to C to D to B to F to G.
A to C.
D to B to F to G, and then you're done.
You didn't do E though.
Oh, didn't see that one.
A, B, C.
Yeah, you can if you jump and swim.
So start there, go on C, go around, walk in A, go up.
Oh no, you can't.
You can't walk
You
around.
literally can't.
This river is infinite.
Ah, darn it.
So you can't go from G to D?
You can go from G to.
So wait, yes, you can.
Yeah.
You can. You start.
Because that bank is the same size.
Can't you just go around?
Start on island D, and then
Okay.
go to E to D. To
Wait,
bridge.
I'm sorry. You started D.
Start at the bridge, the island D. Go to E, across bridge E.
Okay.
Then D, C, A, B. All right.
No, because then you didn't do how would you get off A?
I don't think you can. Yeah. E, B, A. No. I had it. Yeah. E.
Cross the bridge.
I guess it's the least called the bridge problem.
Yeah, it's called the bridge problem.
Yeah.
Yeah, so in 1736, Euler represented the problem as a graph and answered the question. Nope.
He's lying somebody.
Oh, okay. Well, all right. Go ahead. Go up to the board and disprove it real quick. Let's go. You got this, Tyler.
Come on, Tyler.
I didn't
stand
say
up.
it's
No,
like-
you were talking all that smack.
I didn't
on
say
me.
it's like-
Thank you, Leroy.
I was gonna try to put myself in it. That's what I'm doing.
Starting at one land, yeah. Can you cross all bridges exactly once and return to the start? Oh, and return to the start? No. Definitely not. All right. Over the past 200 years, graph theory has been applied to a lot of things. What we got? Electrical circuits, chemical compounds, highway maps,
Oh.
analysis of electrical circuits, finding the shortest route, planning, logistics, genetics, social science. They really need to put warfare up here. One of my favorite algorithms was min cut max flow. And what they did was it was in the 50s. They had a map of Russia's railroad system, and they wanted to know what were the minimum number of points they'd have to bomb in order to completely disjoint, East Russia from West Russia.
Oh Lord. You should have made that a final project.
That would be a fun one, right?
Within that concept.
But then you just implement the min cut and you're done. But that's okay.
Big bomb.
A bigger bomb.
A bigger bomb, yeah, that goes across all Russia. Wow.
Then Russia won't be connected to the rest of the world.
Ouch. Yes.
Ryan said we need to, as part of the project, we need to make an animation of Alice representing our solution.
Oh, okay. Good luck.
Good one.
Okay. All right, let me go back to this picture. I'm going to explain it pictorially what's going on. So all these capital letters are, in this example, are a node. All the lowercase letters are edges. AK, all the land masses are nodes. All the bridges are edges. So this island in the middle is A, a node. The bank on top is C, a node. This island to the right is D, a node. And what's on the bottom shore is also B, a node. Then you have bridges, or edges. One's called G, that goes from C to D. You have F, which goes from D to B. You have E, which goes from D and A. You have D, bridge D, or edge D, that goes from A to C. Bridge C, that goes from A to C. And of course, bridge A, that goes from A to B. And bridge B, that goes from A to B. Okay?
Capitalism. Destroy bridge F and don't use it at all. And then you can do it.
Well played, sir. All right, I call them, by the way, it's node or vertices, depending on who you're talking to. So just trying to make sure you get as much confusing notation as possible at the very end of class.
I love it.
Yeah, not a problem.
Confusing notation.
So let's see. Well, that's not helpful. Really, you're not going to be, okay, great. A is an X. Oh, have you all used these symbols before? I just realized that.
I've used union, but not.
Yeah, subset and stuff. Yeah.
No, you haven't done this. So, well, this might be hard for some else.
Where you get introduced.
Oh boy.
So A is an element, you see that backwards E that's kind of rounded? Is an element of. That thing means is an element of. That thing means is an element of. So A is an element of X. A subset, which is like a U on its side with a little line under it, means every element of Y is also an element of X.
So they're equal to each other.
No.
No.
Because that doesn't mean every element of X is an element of Y. It's just saying every element of Y is an element of X. So for example, let's so if we have 0, 1, 4, this is a subset of 0, 1, 2, 3, 4, 5. Because all these elements are inside of that. Okay? That make sense?
Okay.
But it doesn't work the other way around because 5's in here but not in that one. Oops. Intersection. If you do an intersection of two sets, contains all the elements in A and B. So, if we were to do 0, 4, 9, let's see, intersection 0, 1, 4, 8. That would be the set 0 and 4. Because the intersection are all the elements that are in both. So 9's not in both, 1's not in both, neither is 8. Only 0 and 4 are. So that's intersection. And then union is the other thing. Whoops. How are we doing on the, whoop. There it is. So if we were to, I'm going to just erase this. If we were to do a union, luckily the union is just a big capital U. You would have 0, 1, 4, 8, and 9. Because it's all the elements that are in both. Notice I did not repeat any element. I just listed all the elements that are in it. Any questions yet? I'll tell you where I will keep throwing some notation at you. Why do y'all do this? Ignore that. Ignore the A cross B. I'll let you figure that out later. Okay, a graph is a set of sets. A graph contains a set of two things. One is your vertices, aka your nodes, and your edges, which are the connection between your nodes. So V is a finite, non-empty set of vertices of G. Usually we call them 0, 1, 2, 3, 4, 5, 6, so forth and so on to make our lives easier. E, this is why they did this crossbar notation. All it's saying is that an edge has to go from one vertex to another vertex. That is all this is saying. Okay? It has an edge, it can't go from one vertex to something else. It has to be contained within all the vertices or all the nodes. Hopefully that makes intuitive sense. Elements in E are the pairs of elements in V. Right? Sure. And E are the edges. Correct. So you got vertices and edges. I like to call them nodes and edges. All right. Well, we'll keep throwing some more notation at you. Directed graph or a digraph or ordered pairs, undirected or not ordered pairs. Wow, that is not helpful. Okay. All right, so we have nodes 0, 1, 4, 5, 2, and 3. We can put them in circles. If I were to draw an arrow with one direction, that is called a directed graph. So I can also put one right here. I can move this guy to go right here. This guy could go here, and we could go right there. Hey guys, can you go from 0 to 4?
Yes.
Oh, good. Can you go from 0 to 1?
No.
Nope. It's a directed graph. If it's an undirected graph, that means all these edges go both directions.
Now you can go to 1.
Now you can go to 1. That's undirected.
Oh boy.
It is easier just to think of all graphs as directed, and if they're coming in as undirected, then you just put an arrow in both directions. AKA, we'll erase this, erase that, erase that, erase that, and erase that. So the reason for that, if you wanted to put an undirected edge between 0 and 2, then you just put an edge there and an edge right there. Two separate edges, but that's okay. It's easier to think about it this way. Also, going from here to here may be a different cost than going from 2 to 3. What may help you is think of these as airports. I mean, airports. So Charleston, Paris or something. I don't think there's a direct flight to Paris, but whatever.
No.
You sound like you had something.
I thought it did, but it's from New York.
And just because it takes one, maybe 5 hours, 5 hours going from 0 to 2, it may take more hours to go back for whatever reasons. Which is why it's easier to think of just directed graphs. But if you ever hear undirected graphs, that's what they're talking about. A subgraph is what you exactly think of it. It is, if I were to just circle these 4 nodes with those 2 edges, that would be a subgraph of the entire graph. All right? All right. Good, now we're having pictures. There are no arrows. If there are no arrows, that means it goes both ways.
Okay.
These are all graphs.
Sure are. They're different pictures.
If you're in LA, what's one way to get to Tokyo?
New York,
Dallas, Paris,
To Tokyo. Are there more than one way? Yep.
Dallas, Paris.
You take the long way because it's Dallas, Paris.
They're all interconnected.
San Francisco.
In this graph in the upper right, is there a unique path from 4 to 5? Pretty much, yes. Now directed, here we go, this is a lot better. So if you're at 4, can you get to 1 on the left one? Nope. How about on the right one? Can you get to, if you're at 4, can you get to 1?
Yes.
Yes. 4, 8, 6, 0, 1.
Took me a little bit.
I'm just trying to help you out understand it. Okay, adjacent. Adjacent are two nodes that have an exact edge between them. So, for example, let's consider the one on the right. 1 and 5 are adjacent because there is one edge between them. 1 and, let's see, 1 and 2 are adjacent. 1 and 7 are not adjacent. You can get from 1 to 7, but it is not a direct flight or a direct path. Let's see, 3 and 4 are adjacent. 3 and 5 are not adjacent. How about 6 and 0?
Yes.
Yeah.
6 and 3?
Yeah. Oh, wait, no.
So that was a trick question. 6 to 3 is not adjacent. 3 to 6 is adjacent. There you go. Trick question. An incident that is completely, all right, forget the rest of these. That's nice. A path. I'm trying to really simplify this for you. There's a lot of notation. You're going to do,
Code something like this?
what's up? What's that?
Oh, we have to like code something like this?
Oh, yeah. Oh, this is way easier than a B tree, trust me.
Is it really?
Yeah. Oh, yeah. All right, and we're probably not going to get to it today. We're going to time, but that's okay. All right, a path is exactly what you think of it. It is a set of edges from one to another. So what is a path from 8 to 2? 8, 5. You can't go from 5 to 1.
Oh, never mind.
Oh.
Good guess.
8602.
8601.
Oh no,
No,
you did that.
86012. There you go.
Our powers combined.
Here's a question: are there any cycles or loops?
Yeah, 0, 1 to 2 to 0, 1, 2.
Yeah, so there is a cycle in here. There's some loops in here. Oh boy.
And 0, 3 to 6, 0 to 6.
Okay. All right, we're done with that. Okay, great. Yeah, forget the rest of it.